Okay, cool, nice. So hi guys, I'll be talking about verifiable and private inference, LLM inference, and most of you here probably know that ZK and FHE are the usual answers to this, but I'll talk about different approaches to this problem. Quick intro, I work at DREA as a lead dev, and this research came because we need to have private and verifiable inference, and the people that we are focused on are consumer-grade laptops, like they're just running our program on their Macs or their idle compute. So ZK and FHE are out of the window. TE as well is out of the window. We do quite a lot of things, but in particular, this permissionless peer-to-peer network is where we needed this. And I will actually tell a story of a guy from Finland opened 15,000 machines and tried to hack the system. And then we caught the guy, and he came to Discord saying, hey, I had these points, why did you wipe it? And we said him like, hey, someone was trying to hack the network. And this guy just said, okay, thumbs up, and he left. So yeah, no money for this guy. And you can, I don't think you can read the GitHub link below, but I will also provide it at the end. You can find the entire slides there. I can probably skip this because everyone here knows how widely used AI is today. That's a weird statistics, like 10% of the world population seems to be using ChatGPT. It's a recent research. And we are progressing faster than we thought we were. Yeah, and I will be talking about inference, as I said before. We are not working with training. And at DREA, we also have this thesis that the important thing will be inference, not training at the later stages, like maybe 10 years or something. Like the AGI, if you heard the term, it's like the artificial general intelligence, the one that will likely kill us or something. That will be inference only, and it will be such a powerful model that you can actually, quote-unquote, train it by providing a large context and then do whatever you're doing. It's like prompt engineering on steroids, basically. And what we want to achieve with this inference is we want to be verifiable, as in when I choose a model and I send a message, as in ChatGPT, and I give a prompt, the output, I want to make sure that it really took my message as its input and it used the model that I wanted to use. And with the privacy-preserving inference, we want this model provider to not see what we gave it and not see what it returned at all. This also requires hiding the entire computation internally, because otherwise you can always see what's in there. And as I said, we have this network, and in the future, we believe there will be many open source models, small models, and people will be able to run these locally. So I want consumer grade people to be able to do what I'm going to talk about now. But for that, let's briefly go over ZK FHE in the context of inference. Everyone here knows ZK probably. I'm going to skip this for the sake of time and just show you this slide. So again, I give the model and the message, and the server generates a proof and returns that along with the output. And I hopefully succinctly verify that, okay, indeed this proof is correct, which tells me that they used my model and the message and they gave that output to me. With FHE, you can think of the entire model as a circuit. It's the same for ZK, by the way. And now I actually send my message in an encrypted way. It operates on that without breaking the encryption, and it returns me the encrypted output. Then I can simply decrypt it and read it. And throughout this process, the server has no idea what it was processing on. There's also TE. It kind of achieves both of them at the expense of a trusted attestation server and expensive hardware that also has its own problems with it. And yeah, we can also skip this. I provide some references. I will show them in the end, but yeah, they all have some problems. Some people are working on improving them. One of them is here. So like using finite field in ZK and FHE is a problem for LLMs because we are working with floating point values there. But again, like people are working on it, but today it's hard. I wish it wasn't, but yeah, we have this problem so far. To explain the papers that I'm going to talk about, we need to give a quick primer on transformers, which is like the neural networks that we are using today, most of them. And it's basically what brings the emergent capabilities like reasoning, intelligence. They're not intelligent, but they seem to be so. And this was introduced by this attention is all unit paper. That's exactly, this is how it looks like. This is intelligence. Well, Jan LeCun, a famous guy in this scene, said that if you want actual intelligence, you should not be working on this. So yeah, I don't think this will be killing the humanity, but yeah, it's a really good model. And this is just math operations and matrix multiplications usually. And the most important part is self-attention, which somehow captures the relationship between tokens, like how is the weather today? And you say, okay, today and weather is related, so I should say something about the weather in the next token. And that's how it, all transformers, like. This is from the transformer paper, but I think Llama is using something like this. Like the changes are usually minor or the connections are different. And also I need to say a distinction between the encoder and decoder. So when you provide a prompt, encoder models look at all of it at the same time. And you can think like you can provide for a coding agent, coding model actually, you can provide a function and you can provide the closing brace and tell the model to fill in between. So that will be more okay with an encoder model. But today we don't do that. We only use a decoder most of the time, and that's looking only the previous tokens, not in the future. And it seems to work better, and it has better computational properties. This will make sense for the papers in the future. And another important distinction is prefill versus decoding. So let's say I ask where is Rami library located, and this entire prompt is my input, and that's being used for the prefill. So the entire model prefills the computations, it like fills the matrices, and then it will start the decoding phase, which is it outputs one token and then feeds the entire thing again, outputs another token. This is called the like autoregressive manner. And decoding is slow. Like if you use ChatGPT, it's like blurting words at like a streaming fashion. That's a decoding phase, but the input itself will be used in prefill. Please keep this in mind because this is the entire point of a verifiability paper that I will talk about. So yeah, I want to talk about one simple, really simple, stupid actually, method to detect hackers. And this is how we caught the guy that I talked before, like the 15,000 nodes from Finland. His IP was from Finland, maybe he's using VPN or something, but it's basically, you can generate a procedurally generated prompt, and you can compute the expected output beforehand, and then use just static analysis from the return result. Now, here's a very simple method for this, nothing cryptography related. You have a list of animals, you pick random animals and random numbers, and ask for how many legs are there in this collection of animals. And you can come up with harder questions for better models, but this one is usually easy to answer for even small models like 1 billion parameters. But again, models are usually not clever as you go down in scale. And you will likely have errors here. So you need to have a margin of error, like allow some mistakes and then keep challenging it again and again. But have a more weight on the successful answers, because a fake model is almost always failing. But again, a clever attacker could go around this. And yeah, like I said, you need to have different challenges. And the one thing is quite funny, models really respond in ways that you don't expect. Like that animal question, this is from our database actually. Like this was actually an answer in the network we have. Instead of saying 0, it says no legs. Well, I'm not expecting no as a word, I'm just expecting 0. So yeah. Now moving on to the papers. I'll first talk about this VeriSplit paper, which is like designed for IoT devices. It's just for a preliminary paper because they tried some wild ideas and they're simple but impractical kind of, even though the paper says practical. So one is you can split the matrix multiplications into multiple devices by adding noise to it in such a way that if you gather all of them together, they will cancel each other out. So like W is the matrix and B is the bias, and Y equals WX plus B is the usual operation we do in the neural networks. And you can actually split this into 2 devices with division by 2 and add the same noise to one of them and subtract the same noise from the other one. And if you add these 2 together, you actually get the same result, Y equals WX plus B. For nonlinear computations, you do them yourself. So this means that for each matrix multiplication, you send it, you receive it, do something, and send it again. It's like a hell of a communication there, which is why I said it's kind of impractical. But these guys wrote the paper for IoT devices on your home, like your smart fridge wants to use this, your computer for this process. I don't know why they want privacy in your own house, but still. This is from the paper itself, the figure. So what I just wrote textually is shown like this. And you can generalize this to multiple workers as well, like divide by 4 and add, subtract different times. And this paper was one of the guys who wanted to commit to the intermittent layer in inter-layer computations, which is kind of wild if you ask me, because you are using floating point values here, and you won't get the same results if you do the computation locally. But nevertheless, they wrote the paper like that, and the verifier here will, oh wait, this is an older slide. I had a more sentence here, but the verifier will simply, at random times, do a computation and ask for a miracle proof from the prover, hoping that they got the same result, but this is usually working for integers. And again, this is not a transformer, this is like a convolutional layer, so we want to work with transformers, which is using floating point. Which brings us to the first kind of famous paper on this area. It's the Toplog from Prime Intellect, if you know the company. So what they do is, if you recall the figure, we have this transformer model, which has many multiplications in there. And in there, we have this hidden state, which is where the magic happens, technically. And the hidden state has the dimensions of batch size, sequence length, and hidden size. We can think of batch size as 1 in our case because we are doing inference, so we are asking just one thing. The sequence length is the tokens that we have so far, like how is the weather today has 10 tokens or something. And the hidden size is model specific. It's usually some multiple of the embedding dimension, like GPT-3 has 12,000 hidden size. And what they do is, yeah. So what Toplog wants to do is they want to commit to this hidden state somehow. And they want to do this as efficient as possible. And by committing to this, they only care about the top K values, because the hidden state captures activations of tokens. Like in the sentence, how is the weather today? The weather and today are highly activated because they mean more for the model, and they have more to do with the tokens to be generated. And they're the more important tokens there. So the values are usually 2 bytes, FP16, or can be smaller in quantized models, but let's go with FP16. So you can, in memory, that's just 2 bytes, and you can think of that as an integer. The problem with this approach is the indices, because we are going more than 2 bytes, and we want to use the flattened hidden state. So the sequence length, the hidden dimension, and you do this for each token. And you do this for every few tokens, like 32 tokens in the paper. So that's 32 times the sequence times the hidden dimension, which is larger than 2 bytes. So the Toplog says we could be sending this entire thing to the verifier. So like, hey, here's the hidden state, just do the same yourself. But instead, they compute this injective modulus M, and they map each indices with this modulo M, so it becomes from something larger to just 2 byte values that are not colliding. And then they interpolate a polynomial over this. So we have 2 byte indices that are coming from a larger space, and the 2 byte values that we treat as integers, which are normally FP16, which is a polynomial. Like for top K values, it's a K-1 degree polynomial. And then they send the coefficients of this polynomial only, which is K times 2, actually. And then you simply add the value M and the K value you agree upon before. And that's all the thing the prover does. So yeah, the top right here is the prover. So I send the polynomial, the M, and the output. And what the verifier does is, they do the prefill. So the important distinction here is that this guy does prefill decode. This only does prefill, which is 100 times faster, or more, depending on the output. And that's why it's kind of more efficient for the verifier to do this. But again, they both compute the same thing. And the verifier says, okay, let me look at my last hidden state and see if I get the same indices in your polynomial. And then they simply compare the results. And again, this is using FP16, so it's not like an equals operation there. You do like approximate equal. In the paper, they want exact match for the exponent, and they want some epsilon margin of error for the mantissa bits. This has some vulnerabilities. One major vulnerability is speculative decoding. which is not an attack, by the way. It's a method to get faster faster tokens, where you use a smaller model for the decoding phase, which is guessing, and smaller models are faster at this, obviously. And then you use the prefill, which is faster, with the larger model to make corrections. Google has a really good blog post on this, where they show actual results. Like when you make a Google query, you get the AI answer at the top. It's like multiple times faster with this way. But again, since I'm using the larger model as a prover to do the prefill, the verifier has no way of knowing which model I used for the decoding phase. There are some other internal errors with the paper too. You can fake FP16 by using FP8. But nevertheless, it's an efficient and reliable method. And it has pipeline parallelism support, which I will talk about at the end. And that was for verifiability. Now we go to the privacy, which is it's one of the coolest papers, but I won't spoil it. It has a problem. So there's a paper called Permutation Equivariance of Transformers, which says if you show the entire model as f, and you say like your prompt is x and your output is y, you can actually permute this by some random permutation, and you get the same result if you do the permutation in your input or outside the transformer. Which is cool because, I mean, it's kind of crazy actually. Why this works is row permutations change the order of input tokens. It's like changing the order of words in your dictionary. Linear operations are linear, they don't care about the permutations, and nonlinear operations are element-wise. So again, they don't care about the permutations. So these guys saw that paper and said, what if we permute each layer in such a way that intermediate results cancel each other out, which is why they call it semi-symmetrical of permutations. Intermediate results cancel each other out, and in the end you get one permutation, and at the start you give one permutation. So if I can show you, as a user you provide x, your input, in a permuted way. Some magic happens here, and you get y in a permuted way. And then you get this classifier, which is again has some permutations, and this is your output. It's permuted with pi c, and as a user, you only care about these two permutations, which are vectors basically, just showing indices of permutations. And this actually, for this guy has no cost of computation. They are just using the same model. And yeah, this is the protocol. We have the model developer, which does generates the permutations and send some part to the user and the other parts to the server. And then, oops. And yeah, you basically work over without losing any accuracy at all. But there are problems with this. If user becomes a server, they now know what the permutation is, so they can reverse it. But you can solve that by repermuting the results. But sadly, a recent paper from Ritual broke this attack, broke this method. But at the end of the paper, they say if you use noise, you can actually go away with this. But then another paper says if you're using noise for privacy, you have to have some kind of accuracy loss. So yeah, there's a problem there. And I think that ZK, FHE, yeah, they're cool, but they have some time to progress. But maybe we can come up with better models, better algorithms that specifically are for transformers and for inference. And again, we want them to be for consumer-grade people only. And they are pipeline parallelism safe. Toplock and the STIP paper, they can work together, and you can split the entire model into multiple devices, and they can, again, work together. So that's perfect for consumer people, because instead of one machine you can split the model into multiple machines at your house, like 2 Mac Minis or your smart TV or something. These are references if you want to check later. And yeah, thanks for listening. And questions? Yes. Microphone? Should.
Anyone? Sorry, miss. Fast, please. We don't have too much time. Thank you.
Somewhere you mentioned about locally sensitive hashing.
Yes.
I mean, do you have any, idea how it is used here? I mean, because it's
Um,
mainly based on some making some grouping and having whether it's close to each other.
Yeah, that's just the name of the paper. I don't think it has anything hashing related, and it doesn't also have. They don't have to use the polynomial itself too. Like the paper seems like they're using hashing and polynomial commitments, but they only have the hidden state, and they want to compress that as much as possible. So it's not really a hash. There's no hash function
No,
there.
I know LSH. I know I used somewhere else in my crypto research.
Uh-huh.
They are used for making attack on some crypto mechanisms, but it's just making grouping elements from a large set into subsets. Let me say.
Mhm.
So because they are locally close to each other, and some hash functions are suitable for them, and it's very nice to see again their usage in this area.
Nice.
Thank you very much again, Erhan, for your speech. It was amazing.